Calculus BC students out there. Mr. Record here from Avon High School, and we are at the conclusion of our discussion over L'Hopital's rule. And the L'Hopital's rule that we were talking about isn't your kind, gentle L'Hopital's rule that you might remember from maybe taking Calculus AB, but these are a much more sort of advanced forms of the indeterminate forms that you get from L'Hopital's rule, which would be much more conducive to what you would probably see in a Calculus 2 course. Some of the things that you're going to look at with this video is the fact that these indeterminate forms may not be the kinds of forms that you would necessarily see on the BC exam, but I still think that they're a very important part of Calculus 2 nonetheless. And so we're going to take a look at our example 7, where we're asked to evaluate the limit as x approaches 1 from the right of 1 over ln of x minus 1 over the quantity x minus 1. And the first thing that we want to do is we want to really establish that this is an indeterminate form. Now, I know the title of the question suggests that it would be a form of infinity minus infinity, but I want to verify that. And we can do that by trying to perform a direct substitution, trying to see if we could let that x become 1, at least get very close to 1 along the right side in both of these positions. So if we try to figure out, well, what is 1 divided by the natural log of something very close to 1, but on the right side? The best way to answer that question is probably to look at what the graph of natural log of x looks like. And we should all have a pretty good understanding of that curve. That curve is y equal natural log of x. And 1 obviously is the value that I have right here. So if I say, hey, I'm going to let x get really close to 1 on the right side, it seems like my y value is going to get very, very close to 0. So if I have 1 over something very close to 0, I could construe that as saying that's just 1 over something very, very small. So I would get an infinity value after all there. Now, we can show the same thing for the second fraction, but it's going to be a little easier because we have some value of x that's just slightly larger than 1. But if we subtract 1 from that, we're going to get something that's very small and, again, close to 0. And the closer we get to 1, the closer x minus 1 is going to get to 0. And once again, 1 over 0, or should I say 1 over something close to 0, is going to be infinity. Now, what you cannot do, absolutely cannot do, is assume that infinity minus infinity is 0. Not true. Never will be true. These can be different values, different levels of infinity, and we just can't make that assumption. All right, so once we've established that, what we're going to do now is see if we can use L'Hopital's rule. And if you've watched a previous video, or if you haven't watched a previous video, you learned that if you want to evaluate a limit, let's let x approach c, and let's say that you're having trouble doing that. Well, L'Hopital's rule suggests that if you get an indeterminate form, and that's what I suggest by having trouble, you could take the limit of the derivative of f divided by the derivative of g, and then you perhaps might have a much better chance at having that derivative work for you. So that's what's going to motivate this particular lesson. But the problem that we're faced with now early on is we don't really have this form. We don't have a true f on top and a g on bottom. We have two separate fractions that are being subtracted, and that's a little problematic. And I'd like to address that before we move on. And the best way, maybe the only way to address that, is to get the common denominator of natural log of x minus x minus 1. So the numerator of the first fraction is multiplied by x minus 1. The numerator of the second fraction is multiplied by natural log of x. And lo and behold, we have our denominator, natural log of x quantity, x minus 1. So it seems like we're all set to go with our f over g form. But if we look into this a little bit further and say, well, what if we try to green light or plug in that 1 for x at this point? Without going into a lot of detail, I'll leave it for you to come to the conclusion that this is going to be a 0 over 0 indeterminate form. Now, I want to make a a point here about the advanced placement exam. As I said before, it's very likely that you would never encounter a limit that's going to be this level of difficulty. But if you were to encounter a L'Hopital's rule question that is on the free response portion of the exam, I think it's going to be very important that you sort of delineate the numerator and the denominator. In other words, rewrite a limit with only the numerator and evaluate that by direct substitution. In this case, we would get 0. And do the same thing for that denominator. And again, we would get 0. And then you can show the reader, the person who's grading your exam, that you know that you got a 0 over a 0, which is going to lead to an indeterminate form. And you could even maybe write a statement that says, 0 over 0 is an indeterminate form. Therefore, L'Hopital's rule can be applied. Right? Now, I just did a little shorthand for that just to kind of give you an idea. But I think that's a really great way to tell the reader that you understand the preconditions that need to be met for L'Hopital's rule to be applied, and thus you can then go on to show him or her how it is applied. All right? Now, to continue where we left off, we are sort of at a dilemma here because we got this indeterminate form, but we're needing to kind of remedy that by going into this a little further and applying our L'Hopital's rule. So let's go ahead and see what we get. Let's take that derivative of the numerator. Well, the numerator is going to give us 1 minus 0 minus 1 over x. Okay, that seems pretty straightforward. Now, if we look at the denominator and we attempt to take its derivative, a very egregious, terrible mistake would be just to take the derivative of natural log of x, which is 1 over x, and then multiply that by the derivative of x minus 1, which is 1. That would be incorrect. We would have to apply the product rule because this indeed is a product of two separate functions, each of which contain an x. So I'm going to get rid of that terrible work that I just showed and do the derivative the correct way. Excuse me. So the derivative of natural log of x is 1 over x. Multiply by x minus 1. To that, you'll add natural log of x. Multiply by the derivative of the x minus 1. And, of course, you would just get 1. All right. Next, we're going to go ahead and simplify this numerator and denominator. I don't really see what the numerator is going to do by way of simplification, other than the fact I suppose we could try to get a common denominator, but let's wait and see if that's going to be absolutely necessary. For the denominator, I'm going to distribute my 1 over x into both of these terms, so I would have 1 minus 1 over x, of course, and then I would add my natural log of x. All right, well, let's see where we're at. If we, at this stage of the game, try to directly substitute x equal 1, we see that this would lead to 1 minus 1 over 1, which is going to be 0, over 1 minus 1 over 1 plus the natural log of 1, which is 1 minus 1 plus 0, which is also going to be a 0. So we have another indeterminate form. And it really doesn't matter how many times you get an indeterminate form, but you can apply L'Hopital's rule in as many instances as you need. So that's what we're going to do. We're going to use L'Hopital's rule again. So we still have the limit as x approaches 1 from the right. We take the derivative of the top, which is now 0 minus, and then when we take the derivative of 1 over x, we can think of this guy as kind of dreaming as being rewritten as x to the negative 1. So the negative 1 times the negative 1 would become positive, and then we would lessen the power by 1 to get x to the negative 2, and of course we could rewrite that as 1 over x squared. So there's our numerator. The denominator would have something similar, 0 minus, and then we have another negative 1 over x squared. So positive 1 over x squared, we'll call it. And then the derivative of natural log of x is 1 over x. So we feel like we've taken that derivative correctly. Now let's see if we can directly substitute. So if we let x equal 1 this time, the numerator gives me 1 over 1 squared, which pretty much guarantees that I'm going to avoid an indeterminate form. We think that this is going to lead to our answer. The denominator, of course, would be 1 over 1 squared, or 1, plus 1 over 1, which is 1. And we end up with this wonderful numeric answer, 1/2. And that is going to be the answer to the limit. Now, if you have certain pieces of technology at your disposal, you can check this answer a variety of ways. And I'll show you just one of those ways here in just a moment. All right, well, here we go on the TI Inspire. I've taken a moment to sketch the graph in the f1 of x function menu. And I've got, I don't want to call this a kind of a boring graph. It's not too terribly interesting, I would suppose. But nonetheless, this is what we've got. And I could do a variety of things to kind of verify what's happening here at x equaling 1. One of the things I want to point out is most graphing calculators, the TI Inspire is no exception, is going to have some issues with kind of separating these removable discontinuities that we would have in a problem such as this. So I want everyone to understand that if x were to equal 1, we've got some big problems. And you can see that the curve doesn't really show any kind of a discontinuity there, but yet we have to understand that there is one. One way I could demonstrate that is if I could call up a table, and I can look at my table where I have the x value of 1, we can certainly see that the y value is undefined. But if I wanted to get kind of close to this 1 from the right side, I find that I'm limited with the Inspire's natural default settings. I can get close to 1, but only 2 would be the closest that I can get with the default settings. So if I just simply go into the table settings and decide to edit them so that the independent variable is set to ask, then I have free reign to get as close to 1 from the right side as I wanted to. So remember the 2? I can probably get even closer, like maybe 1.5. How about we do better than that? How about 1.25? Can I get closer still? Certainly. 1.1, 1.01, 1.001, etc. And you can start to look at the value that we have for y, and that it seemingly does approach the 1/2 value. Now, because the calculator that I am dealing with is a CAS calculator, computer algebra system, I could take this function and I can actually allow the calculator to take its limit. So I'm going to see if I can just copy and paste this so I don't have to retype it. So I'll hit Control-C, and I'll go to a calculator scratch pad, and I'll say, well, let's find this limit. Let's take the limit of the function that I'm about to enter as x approaches 1 from the right, and that function is in my clipboard, so I'll hit Control-V, and I can find out that the calculator is going to give me the correct answer of 1/2. Now, this is not meant to be any kind of solid proof. It's just demonstrating the CAS features of a calculator to see if whether or not our answer was correct. And here we are correct. So anyhow, I hope this video helps out. There's several more in this series of advanced L'Hopital's rule. I invite you to all check them out. And until next time, good luck, everyone.